It's way too much time, way too much computational time. You can scale it down, and as long as you keep the dimensions to scale, your simulation results will be meaningful.
Okay, so this is going to be our first step. Does everyone have a workbench open?
Yep.
So it's going to look kind of like this, but without the, it'll just be a blank white space.
Yeah. So Ansys is I was telling them a little bit, but Ansys is actually a family of softwares. There's a bunch of different softwares under Ansys. This is called Ansys Workbench. Mm-hmm. You can see it here. This is Ansys Workbench. It's a nice like software on top of all their family of softwares that essentially just compiles everything together into one package. So instead of having to like open up the geometry software, save it, close it, find the file, open up the meshing software, port the file in, this does all that for you.
Mm-hmm. Okay, so our first step is going to be creating the fluid for Fluent because there's so many softwares it can kind of get hard to find stuff. So we're going to look for fluid flow and then Fluent with Fluent meshing. We're going to pull that and drag it out into this white space. And that creates this, this system. And this kind of goes over all the steps again. You have your geometry, you have your mesh, your setup, your solution, and your results. So this compiles all the applications in the one spot.
Does everybody have this so far?
Mm-hmm.
Cool.
Everyone's good? Great. All right. So now we're going to right click on geometry. And this is where we're going to import that geometry file we have. So you're going to right click, go down to import geometry, and then I guess click browse so you can find it. And it'll be in your OneDrive. Too much stuff in here. Ansys workshop files.
While he's finding the file, a little tip, because I know probably most of you work with SolidWorks. Ansys does read SolidWorks, but it does not read SolidWorks files. If you just try to upload a SolidWorks file purely into Ansys, it won't read it properly. So when you're saving your SolidWorks file, save it as an IGS. It will look like .IGES. For some reason, whenever they pronounce it, they skip the E. But it's called an IGS file. That is kind of like your generic CAD file. It's like a .png. Instead of having a Photoshop file or a like Microsoft Paint file, it's a photo file. Except for CAD. .IGS is what you need to upload.
Yeah.
I'm getting an error that the selected files have been unsupported or unconfigured.
It worked for me. Is it maybe the year? What Workbench is download? Like when you open up Workbench, does it say 2024? Okay, so you guys have the same Workbench as me. Yeah. Try downloading the file off of the OneDrive onto the computer, then importing it.
Yeah.
Yeah.
Yeah. So it still doesn't work.
.ds.
DSCO should also be accepted.
They don't have Discovery on there for some reason.
You don't have Discovery?
They don't have wait, no, they do have Discovery.
You don't have Design Mod?
It's okay. This is a Discovery file. So everyone, wait, do you have Discovery when you right click?
Okay, guys. So when you right click geometry right here, do you see Discovery, Space Claim, and Design Modeler?
Yeah, they don't have Discovery. There's another file I can give.
Hold on, wait. You're talking over him. It's just what?
They don't have Discovery.
Okay. You have Discovery?
All right.
So can you convert that?
Yeah, there's another. Wait.
So Discovery, the Ansys has 3 different CAD softwares in it: Discovery, Space Claim, and Design Modeler. If you're using IGS files, you can upload it very easily into Design Modeler. If it's I prefer Design Modeler, but Ansys, the new one is Discovery, and Ansys really is trying to push Discovery, but I don't think it's as good as Design Modeler personally. But for the tutorial we're pulling from, it also is using Discovery.
They also had this file. It's the same geometry, but it's a different file type. Try this new file I uploaded, model airplane 2. It's a SCDOC file. See if that works. It's the same geometry. Yeah, it's in the same folder. So you might have to download the folder again though. Let me try to see if that file worked. Okay, that file worked great. Yeah, so I don't know why Discovery's not on these if it has the same workbench.
Which
That's
which
weird.
did you open it in?
Model airplane, the SC dot.
Well,
So you imported it and it worked this time?
yeah.
Cool.
You guys don't actually need to open the geometry.
Yeah.
Because we'll see it in the mesh. Okay. So has everyone got that new file imported or is anyone having trouble? You guys got good? Great.
Cool.
Okay. Sorry about that.
Yeah, that's honestly really the biggest hurdle with Ansys is
Yeah, they use like 10 different applications for everything. I don't know why.
Yeah, there's 10 different applications for every single application. There's so many different file types. The biggest learning hurdle with Ansys is moving around Ansys.
Okay, so does everyone's screen look like this? Is there a check mark in your geometry? And then there's like a little circular check mark.
All right.
All right, so now we're gonna go down to mesh. Well, actually, let's talk first. Present. All right, so now we have imported our geometry, and we're gonna talk about some aspects of the geometry. The fluid domain was already in this geometry file, so we're not gonna make it, but we'll talk about it because this is very important. So the things to consider in a fluid domain. It's the size of the domain, very important, because if you have an aircraft, like, but you have your walls of your fluid domain too close, the flow is going to interact with this wall, and then you're going to get bad results. Really bad drawing.
You don't want the air that's hitting your aircraft to come up and bounce off the top of your fluid domain, because in reality, there's no real wall there.
Yeah.
So you don't want any interaction there. You want to have it far enough away from your aircraft that they don't interact. How far away depends on your aircraft. Meshing is the one part of the CFD process that is not a science, it's an art. You kind of just got to mess around and find the right value. Typically the standard is like 5 to 10 chord lengths of your aircraft, distance wise, should be enough. If that's still not working, or if your computation is going too slow, you can always go back in and change the size of the fluid domain to either cut down on computation time. Smaller domain means shorter time, but smaller domain tends to also mean more bouncing, if that, yeah.
Yeah. So the size, but also the shape of the domain. So there's a couple different types of domains. There's box grid, which you can see over here. It's a box. And so this is used a lot with cars because you actually want the wall effect when you're a car, because the car's on the ground, they're not in the air. So you need to simulate the effect the ground has with the car. And also if you're simulating an aircraft and ground effect, which is when you're close to the runway, you get some effects coming up from the ground, which affects the aircraft. So that's a couple instances you use it. You could also use it if you're trying to like be more accurate on validating wind tunnels, because it's closer to the real shape of a wind tunnel. And then there's O-grid, which is used a lot when you need changing angles of attack. So, because instead of like because you have an aircraft, so you have it modeled at 0 angles. Instead of remeshing every time you want to do 10 degrees, 20 degrees, 30 degrees, you can just change the components of the velocity coming in. So instead of changing the aircraft, which then you have to do a mesh again, which takes a very long time, you can do that. The air comes in at 20 degrees below it. So you get the same effect, but to do that, you need an O, so it's not interacting with the walls. Because if you would do it on the rectangle, it would hit the walls, and then you.
So to illustrate this, if this is the front of your fluid domain, if your air is coming in at straight lines, it's going to follow along, and it's not really going to interact with the top. So that's fine for this. But the moment you start trying to typically how we do angles of attack is you don't actually change the position of the aircraft, because then you got to remesh, you got to redo everything, a lot of work. So instead, we change the angle of the air coming at the aircraft to do that. And if you're using just a straight like cube like this, and you start having your air come in like that, this little pocket right here is immediately going to interact and hit the roof. So you can get around this by, instead of having a box, if the front is like a dome, you can have your air coming in at any different angle you want, and it's not really going to hit anything.
And so this is kind of what he illustrated. This is called a C grid. So it's kind of combines the sphere grid and the rectangle grid, because it allows you to still get that changing array, but you can still have the rectangle going downstream. And it gives you also, rectangle gives you more flexibility in defining how far it is. Because let's say you don't need it as far from the start, but you want a lot of distance downstream because that's where the flow changes. Mm-hmm. So you can see in this instance, whatever they're simulating is right here. So it's much closer to the front than it is to the back. But with an O, since radius is constant, you can't, you have less control over that. And then also another thing we do when we're doing our domain is we use symmetry to cut down on computational time. So if you have a wing, instead of simulating the whole wing, you can simulate half of the wing if it's symmetrical on both sides. And you get the same results, and then you would just double the results for your final result. And I mean, so that kind of comes down to a certain point is you could keep cutting it down if the wing's completely a rectangle till you get to an airfoil. But
same thing with aircraft too. If your aircraft is symmetric down the center line, which most are, you can just cut the aircraft in half, just delete everything on that side, all the fluid domain, the aircraft, everything on that side, and just do that half of the aircraft and run the simulation that way and take out literally half your computational time by just doing the symmetry.
All right, and so now we're going to start talking about types of meshing. So Dr. Sean already went over this a bit, but there's structured grid and unstructured grid. And structures are usually squares, they're at least four-sided, and then there's triangle grid or hexahedral grid. And so the differences between these is unstructured is much easier to get around a complex geometry because you don't need to divide it up into sections, but a structured grid cuts down the computational time and is usually more accurate. And then this is a big thing, mesh quality. This can affect your results a lot. So there's a couple of different values that I measured with this. There's orthogonality. So this is like the perpendicularness. Is it straight with the flow? Is it completely perpendicular with the flow? Or is there an angle to it, as you can see here? And then the skewness. So this it's kind of similar. Is it at an angle? And you can see you want it more up straight instead of canted over. And then there's relative size. This is a big one, is you want cells. So these are called cells. You know how the mesh is split up into very small squares usually, and then each of those is called a cell. You want the cells next to each other close to the same size. Like obviously they'll be slightly different, but you don't want to jump from a small cell to a big cell because that will give you a large gradient and that can mess up your results. You'd want to, let's say you want larger cells out here, then you do like a slightly bigger cell, slightly bigger cell, slightly bigger cell till you get to that. And that comes in a couple different factors you can define, like growth rate, and that will say how large it gets. And these are kind of values that Ansys gives you to keep under. So you want to keep your aspect ratio, which is the largest side over the smaller side for a square, under 5. Your element quality, which this isn't really something you can define. There's an equation Fluent uses, but they give this to you and it's 0.05. And then same with orthogonal quality. And then your max skewness is 0.9. So you don't want it at too high of an angle. And then here's one thing. We won't do this in this workshop, but if you want to guarantee the accuracy of your mesh, you have to conduct a mesh independence study. And what that is you simulate multiple meshes. So let's say you have one that's 1 million cells, one that's 2 million, one that's 7 million, one that's 12 million. You keep doing this and keep making it bigger until your results stop changing. Like, because as you get bigger, you'll be slightly more accurate, but you're also adding a lot of computational time. So you wait till this result stops changing, and then you use the smallest mesh where it stops changing. So you can cut down on computational time and still guarantee accuracy.
For most club work, you might not do mesh independent studies. You just want to make sure you have a relatively high number meshing. If you're using the student version, 1 million cells is your limit. You can't do more than that. To give you a ballpark for what that's like, in my research lab, and I have the professional license, I typically work with like anywhere from 1.7 to 2 to 3 million cells on my research topics. So 1 million is limiting it, but not too much. I mean, I'm doing research work. For club work, you can be a little bit less accurate. And mesh independent studies take a while because you literally have to remesh it every single time and run it and compare the results. If you're not doing a PDR or something that might call for a mesh independent study, like if they don't tell you to do one explicitly, probably shouldn't worry about it.
Yeah, this wouldn't be really applicable for the club, but I would just, if you are doing this on your own and you want to get into accuracy. All right, so next thing is we're going to talk about boundary layers. And so this comes into a big effect when you're determining your mesh, because as you guys know, if you've taken fluid mechanics, close to the wall, the velocity is 0, or at least if you assume no slip. And then it gradients upward, and you can see this is a sharp gradient. So this is a steep changing velocity, but then it shallows out. So you need much smaller cells down here to capture that gradient, but as you get farther out, you can use larger and larger cells because it's not changing.
It's the boundary layer that really makes wings do the things that wings do.
Yeah, so you want to resolve that properly, or your results can be off by a decent amount.
If your if your cell height is bigger than your boundary layer height, it won't simulate it. So that's something you got to kind of hand calculate a little bit and check yourself.
Yeah, and so the way we capture this gradient, if we're doing an unstructured mesh, because unstructured mesh, you can't get the cells as thin as you want down at the boundary layer. So you have to incorporate something called an inflation layer, which is basically it's a structured mesh. It's a combination of structured and unstructured, but it's very thin cells at the wall, and it has a growth rate where it gets larger and larger until it transitions back into unstructured.
If you're doing a purely structured mesh, though, you can't do an inflation layer. You'll have to manually try to shrink the size of your cells at the point of contact with the airplane or whatever it is.
The inflation layer is just a part of a structured mesh. The inflation layer is the mesh because you just incorporate it into the same.
The inflation layer is a tool that you can use in Ansys to manually put a structured mesh right where you want it.
All right, so now we're going to move on to creating our mesh. Here's the steps, but I'm going to have to close that so I can actually show my screen. So we're going to go to mesh. We're going to right click on that. We're going to click edit. And this screen will pop up. So this is the Fluent launcher. You can select double precision. It just gives you slightly more accurate results.
You do want double precision, by the way.
And so down here is meshing processes and solver processes. So this is how many cores of the computer Ansys is going to use. I'm not sure. We can actually do that real quick. So if we go to Task Manager, I don't know if you get access to Task Manager on those.
Huh?
This one has 24.
That one has 24?
Okay, so unless you're an admin on school computers, you typically can't access Task Manager.
Yes.
If it's your own computer, Task Manager, you can go to CPU and look up your core number.
Yeah, so if you're on your laptop, like, so for instance, I have 8 cores, but each core can do 2 processes, so you have 16 logical processes. So that's really the number you can use. Obviously, you don't want to use all 16, or the rest of your computer will shut down.
Yeah, don't use every single processor.
Yeah, you want to leave a couple for your computer to run.
Because then your computer won't run.
So I'm going to use 4 since I'm running like PowerPoint and stuff in the background, just so I don't accidentally crash it.
Yeah, if you have any tabs open on your computer, if you have anything open in the background.
If you guys have 24, you guys could use like 12 or something. It'd be slightly faster, but yeah. So we'll click Start down here.
Another thing is Ansys typically takes a while to load because it's just a very deep processing software. It's heavy.
All right. So now, do you guys have this screen? Like
No, he did 4 processors for both.
I did 4. Yeah.
You can do 12.
You guys could do 12 maybe.
Do not put 24. Your computer will die. That's what this.
But do 12.
You can do 12. Yeah, on yours.
You guys all do 12. Yeah.
Yeah, 12 in each. Yeah.
So you guys will run faster than mine, so I'll be waiting while you guys all have it.
Yeah, so one thing to watch out for, Ansys is very customizable with its settings. As you've seen, you can even pick how many processors the software is gonna use on your computer. With that level of manipulability, you can really customize your results. It's really nice. It's very hands-on to get exactly what you want. The downside is very easy to just blow up your computer. Like the other day, I was working on literally just drawing a line across one of my surfaces, and I was trying to designate how many points I wanted to the line. I said 100, and I wasn't accurate enough. I did 200, not accurate enough, and I was just got bored, so I said do 1,000 points. My whole computer crashed, and I lost all my progress.
All right.
You don't jump the gun. Even if it's going slow, go slow.
You gotta risk it.
Oh, I saved beforehand, but the file corrupted. That's the problem. Yeah, you gotta make sure you don't just like throw everything you've got at Ansys, because it will take everything and more.
All right, so if everyone could go up to import geometries, and you should see down here, since we already imported the file name. Does everyone see that in file name, like it says airplane?
Everybody got the file name down there?
Yeah, like down here.
Cool.
All right, great. So now we're just gonna go down to import geometry, and it'll take a second to load. Might be faster for you guys. Yeah, and also, yeah, so laptops kind of, you can do it on laptops, but it obviously isn't the fastest.
There you go. The waiting game. Has it pulled up for you guys yet?
No.
No, that's
Okay.
fair. Oh,
What? Oh, it's because it's a space claim file.
Yeah,
I've never
wow.
used space claim before.
yeah. If it asks for access, say yes.
You guys, it should already be.
Yes, it should have access because it's a school computer.
I don't think I've ever opened space claim before, at least since I've downloaded the 2024 version.
I don't know why Ansys has 3 different CAD softwares, but whatever.
Okay, looks like it's about to get up here. Nice.
There we go.
All right. Do you guys see a dome? No. Okay. Well, I'll give you guys a bit to load. But I guess while it's loading, we can take a look at the geometry itself. So I'd first click on this face. And so it turns green when you select it. And if you double click this little eye, it will hide that. So you can see the actual aircraft. And boom, it's red and blue.
So click the dome surface. When you click it, it should highlight green.
Yeah.
And then in the bottom
Yeah,
of your
let me redo
screen,
it. I don't know how to get it to show it. This ads. You can get.
there you go.
Okay, so does everyone have this on their screen? Okay, no, is yours just still loading?
I get a CAD error on my computer.
What?
I got a CAD error on my.
Yeah, CAD error.
Are you remote accessing or something? Oh, okay.
Did anybody else get a CAD error?
So you don't have the CAD? Did you get it in here or did you get it in what?
I got what I'm trying to do.
Does anyone else? Hey,
No.
do you have space claim on your lab computer?
Yeah, I mean it's our lab computers. They should have it.
It's not high.
Yes.
So yeah, from anybody else, if you see this and you select it, it should go green. And then down here, this little eye with that line through it, clicking that will hide that.
It should work for you since, yeah, you have discovery.
Yeah.
That's
Can I
right.
hide in mine?
You double click this little eye.
It's
with
not
like the little
Oh, yeah, no, you gotta double click the eye for some reason. I don't know why they think the eye button,
Thank you.
double click.
Is everybody right here? Has everybody gotten this clicked besides Ken? Raise your hand if you don't have it. Cool. So we're all waiting on you, Ken.
Okay, yeah.
Okay, we'll move on. Yeah,
Alright.
Ken works in our lab too. All right, so then you double click.
You want to hit it? I think everything was selected.
Oh, I selected everything?
Here, I got it.
No, I only selected that.
No, you had it. It's because I just showed. It was already all selected beforehand.
Oh,
Okay, so If you hide that, now you can see the actual aircraft. It's not covered by its domain.
You can see here that it's cut in half.
Yeah, so look, there's nothing over here. It's hollow. And also, a thing you do is you make the region of the aircraft hollow, so the air will just flow around. It's just like a void.
There's two ways of doing that. You can either, when you're CADing the soft, like in SolidWorks CADing it, you can do like a thin surface and make it literally hollow. Or when you import it over and you're putting it inside the fluid domain, because there's, depending if you're using Space Claim or Design Modeler or Discovery, the exact how you select this tool might be different. You can just look up how to do it, but essentially what you want to do is you take the your solid of your aircraft and you take the solid of your volume and you subtract the aircraft from the volume. So it should take the aircraft and cut a hole in the volume, the exact shape of the aircraft, and then delete the aircraft.
Yeah. All right. So our next step is we're going to go to add local sizing. And so you can see kind of all the steps are going to be in order. So it's nice and easy to follow. You go down here. Would you like to add local sizing? Select yes. And then you get this screen that pops up. And this is a face sizing. So the faces we're going to size are the leading edge and the trailing edge because they're very sharp. I can show you guys like why we're doing this is you can see it.
So specifically what we're doing right here, if you just hit mesh, it will create a mesh for you, but it'll do a randomized unstructured mesh. You then go in to these settings under workflow and you're doing what's called mesh controlling, where you're selecting certain areas, certain surfaces, and designating, hey, Ansys, don't just put a random size element here. I need the elements to be this size on this part of the aircraft.
Mm-hmm. Okay, so we have, so you can see this leading edge is a sharp edge on the aircraft. So we need to have small cells to properly mesh sharp edges, or they get defeatured. So do your target mesh size down here. It should be in meters. If it's in meters, type in 0.01. For some reason, your millimeters, just convert that. And then we're going to go down here to select by. And so this is where you can select the faces. The face is already named for it. So we have our fluid, which is the full region. Fuselage, which is the fuselage, and then, wing and stuff. But we have wing leading edge and trailing edge. So wing LE and wing TE. We're going to select both of those.
If you were doing this manually yourself and building the domain, what you would do is once you've like subtracted it and you've gotten your domain and everything set up, you would go in and click like the leading edge, click the trailing edge, and you would name each section, each wall, leading edge, trailing edge, wing, aircraft, fluid. And Ansys will actually recognize that English. They're like, oh, you typed in fluid, this is a fluid domain, and it'll set up things for you.
All right. So we're gonna click add local.
When you're doing the name selections, do you do that after you've done the Boolean subtraction?
Yes.
Yeah. So you would do it in the geometry. You can select faces in the geometry modeler. There's a option where you can select, where you just select faces, and then you can do it like, let's say you want to select the whole aircraft and name all the aircraft. So if you click that, you get every single face on the aircraft. Or you can name it, trailing edge, wing, fuselage in there. And then when you also get to the results phase, then you can plot just on the fuselage. If you want to see results just on the wing, just on the fuselage, you need to name it beforehand, or you won't be able to divide it properly.
The naming is the last step in the geometry process.
You can also do it in the meshing process if you want, but it's usually easy to do in the geometry.
Yeah, you can also, when you import it over to meshing, you can, if you forgot to do it, you can still name it here, but name it before you mesh.
So we're going to click add local sizing. Does everyone have 0.01 meters and then selected wing, leading edge, and trailing edge? All right, great. So click add local sizing, and then boom, we have a local sizing. So we're going to add another refinement, and this is going to be a body of influence. So we're going to go to insert new task. Well, first right click on add local sizing, insert new task, and then we're going to go to create local refinement regions. So this is going to create a region of refinement. So it's going to be smaller cells around the aircraft. So we have this.
Question?
You said click add local sizing at the bottom, then right click add local sizing at the top.
Just right click add local sizing. And then you should get a screen that looks like that. So if you right click, that top local sizing, and then insert new task. And local refinement regions should be here. It's not there since I've already clicked it, but it will be there if you haven't clicked it yet. And then you get this down here, which says generate local refinement regions, and this is where we'll define our region. So we have
Right, where was that?
the local refinement region, right below face size.
Okay, yeah, there you go.
It's in the same region. So we have right below face size we have local refinement region, and then so you have your name. We can leave that.
Try slowing down your mouse movements a little bit. It's like lagging on here, so it might be hard for them to see.
Okay. So and then we have type. So this it defines what type of refinement region we're going to do. So there's box where you would just define the dimensions of a box around it, but we're going to do an offset surface. So everyone do that and then click offset surface. And then we get this. Let me double check the dimensions we're supposed to define. So you can see I spelled out all the stuff we should define beforehand. Local select offset surface 0.004 for the mesh size. So we're gonna go here, and mesh size will be 0.004. Yeah, and so leave select by label, and we're gonna select all the regions of the aircraft. So fuselage, that's the first one. Keep scrolling. Wing, so we have our wing, and then our leading edge and our trailing edge. So now the whole aircraft should be green. Right? You good, Thomas?
Can you go over what the select again?
Yeah. So we go to the select region, and then fuselage, wing leading edge, and wing trailing edge. And then your whole aircraft should turn green. That's showing you've selected it.
Yeah, I can't select it for some reason.
Yeah. So you have fuselage selected, I believe. Well, click on it again. Yeah. Yeah. So click that. Wait. Control click it. Sorry. I'm not, yeah, you don't need to. I'm not sure why.
I only have the hairful.
You only have the what?
Something went tragically wrong. And I'm not really too sure what happened.
Oh no! What the heck?
Well, I see it.
I have no
Yeah, let me
idea. I
Uh,
already tried it on iPhone.
Oh, there we go.
I have no idea.
Okay, here we go. For some reason, I don't know what wildcard means, but for some reason that wasn't letting you select it. So now you have all of it selected.
okay.
I did you choose 0.004?
So that's just resizing it. So I mean, relative to the aircraft, it's going to be kind of different. I made it actually larger than what the tutorial was using, since I wanted to keep the cell count lower so we could run it faster. What's your problem?
I have no idea. I don't
I
even know.
have not seen that.
Yeah, if you double click on it. Okay. Actually, wait, click this button. Yeah, so this actually lets you select which one to show. So if you just select everything but the far field. So select like all of, well, except the far field and the fluid. Yeah, no, I don't think don't select the fluid. Select like the fuselage, the second. Yeah, there you go. You have to zoom in. Oh yeah, there you go.
I didn't know.
Yeah, here's this one quick.
But I think I did it on.
There we go. Now, yeah, hit apply and display. There you go. Now you should, if you zoom in real quick, you should have the apply.
Yeah.
Alright.
Hey, Andrew, these two have done something really weird. They, like, what is? What? No, oh yeah, you can't,
Did you guys delete? How'd you get?
Yeah, so somehow in the midst of hiding their dome, they turned everything into a triangle.
Try closing it, it should be open. Maybe on
Yeah. Ultimately, if Ansys just gets too messed up, close it. Yeah.
So I'm about to go.
Mhm. Oh, so
All right. Well, we're gonna
you can
keep
email
moving.
Dr. Sharma.
Well,
You can ask
I'll
him-
help you guys like later if we can. So we have 0.04 for our mesh size, and does everyone have the aircraft selected that can? All right, great. Yeah, perfect. So it should be 4 things you have selected. All right. So and now we got to define our flow direction, which will be X because you can see X moves along with the aircraft. So we can leave that. Defeaturing size. So this is the amount of size the geometry will defeature to match the mesh. So we want to bring that down, I believe, to 0.02 meters.
So the Ansys, if you tell it to do a mesh size of 1 millimeter, so make every cell 1 millimeter, it won't do that. It'll make every cell about 1 millimeter, and it'll do like a range of that. You want to control that range, and that's what the defeaturing it's called in the software. It's called defeaturing.
All right, and so now we have boundary layer height, and this isn't the boundary layer that we're talking about with Fluid. This is boundary layer for the refinement region we're making. So we're using offset method. So what's it gonna do? We defined well, actually, this will be defined. So this will be 0.2 meters, and so what that means basically is a region that's 0.2 meters offset from this aircraft. So it will kind of resemble the aircraft. It will look like a cloud around it. Will be more refined than the rest because closer to the aircraft is where the flow is changing. So that's where we need cells to properly resolve it. Boundary layer levels, we're gonna have 2. So this means the first level, so it's actually gonna be 0.4 meters now. The first level is gonna be that original size, but then the second level is gonna be 2 times that, so 0.008.
Let me explain this one more time. So you don't want every single cell in your domain to be the same size because you don't need to really calculate as accurately the stuff going on really far away from the aircraft. You don't care about that. You care about what the air is doing and interacting with the aircraft. So what this refinement region is doing is it's creating a region around the aircraft where we're telling Ansys, make any cells you generate in this area smaller and more accurate, and don't really care as much about the cells outside this area.
Mm-hmm. And then we're going to do wake levels too. And a wake level is basically the same thing as a boundary level, but it's times 4 now on the growth rate. So the first boundary layer will be 0.08 times 4, then the second one will be that times 4. So it's a way to have a transition because you don't want the very small going with like the far out cells, which are large, because then you have the problem with sizing.
Yeah.
So you want to give it a rate where it grows smoothly.
What was the
Defeaturing
featuring size again?
size was 0.02 meters.
What is that?
Oh, yeah, sorry. So defeaturing size, because you're splitting into small subregions, so you can't exactly model the geometry. There's going to be small like defeaturing. So that limits it to 0.02. So the geometry we have now won't be any different than 0.02 after we apply the mesh. So the smaller the defeaturing, the more accurate, but also the more cells it's going to have to use to properly model the curve. Because if you do like an integral under a curve or Riemann sum, where you have multiple, it's not going to properly get it. So it's like a Riemann sum, and you're trying to get it as low as possible, but obviously there's limits to our computational time. So this should all be, I believe, growth rate we leave to
Did that answer your question?
1.1. All right, yeah. So in growth, yeah, okay. So and then weight growth factor should be 2. I believe it's default to that. So now we can click create local refinement region. Boom. This will take a second. Everything in Ansys takes a second. All right, there you go. Yeah, so you get like this little cloud, and so it's offset, however far it's offset. But you can see how it goes further out in the back because that's more important. And then it gives you an offset around top. So this is a way I like it better than you can also just do a box around the aircraft where you have it smaller. But I feel like when you do the box, it doesn't properly like transition into a.
You got sharp edges.
So this,
along the
yeah, this
box.
gives you like a smoother transition between meshes. So now I believe we're going to generate the surface mesh. So go down here to generate surface mesh, click that, and you get these boxes. So these boxes are the cell size you have defined. So obviously, I believe this is the max size. So obviously 1 meter is too large. We don't want the cells larger than the aircraft.
Yeah.
So we're going to define them as min size will be 0.002. So that will be the first box. And so you can see when you click on min size, it shows you the size. So this gives you a good reference on knowing like how large your cell should be. And then max size, well, max size will be 1 meter, but that will be like out here. Yeah, so you can see 1 meter is more reasonable far out, but down close to the aircraft, it won't be. Why did this show back up?
You gotta hide the dome
Yeah.
again.
There we go. And then generate surface mesh with curvature and proximity. So yeah, so for size function, we're going to use curvature and proximity. And then our curvature angle will be 12 degrees. And so that's defining the kind of the angle the cells will max like curve at. So you want to keep that low.
Yeah, just like in all this, every time you go from one cell to the next, you don't want a big jump or a big change. So this is limiting the, like, even though they're going to be slightly angled every time, it's making that angle instead of going from here to here, from here to here to here to here to here, just making it a nice smooth transition.
And all this stuff, it's kind of stuff you have to determine on how small the cells will be. It will be looking up, like, you can find other people's simulations, what they've done before, and if it's similar to what you're doing, you can use similar sizing. But also, you got to think about they have better computers than you. You're going to have to make your cell count smaller. So does everyone have this on their screen for generate surface mesh 0.002 for minimum size? Max size is 1 meter, 12 degrees, and then curvature and proximity for the size function. Okay, so Grant, you actually want to go help them? Sure. So I can keep going. So now we can select generate the surface mesh. So this will generate the mesh on the surface. So this will be a 2D mesh. So we click that, and this will take a second. So you get a little loading by now. Is everyone's loading? Do you guys see like at the 10%? All right, great.
It's just too small. He's trying to do the refinement region. I think he's using too small of refinement.
Okay, do offset. Do mesh size of 0.00, was it 2 or 4? I forget. It was 2, 0.002. The featuring size of 0.002. Let me go check my PowerPoint. Oh, did I get serious?
No, it's just a really fun mesh.
I don't know why it's doing. I did the same exact settings before, and I got a good quality mesh, but I'm not sure what.
Oh, did you hit mesh and look? It went dark all of a sudden. Yep. So that's because it's showing you every single line and edge of every cell, and if you're zoomed out too far, it'll just look flat.
Yeah, because the cells are so small, you can't really see the subdivisions when you zoomed out. So it will look like this. You can see the different refinement regions we have, how it gets larger and larger the further you go out. And as you zoom in, you can see the actual mesh of the aircraft.
Yeah.
So you can see the trailing edge is meshed pretty well. So we have a good surface mesh now.
There you go.
By the way,
We're doing.
Oh wait, actually the quality wasn't bad. It was talking about my camera view for some reason.
What's next about
Yeah.
is there a way to like pan?
Yeah, I believe it's control and then hold down scroll mouse, and then you can pan around.
Okay.
What were you saying?
Can you pull up the
Yeah,
that's
the
the
size.
cloud?
Yeah, so the offset size is 0.004, or the mesh size. So that's the first one.
He's doing a surface mesh now.
Oh, he's doing a surface mesh? Okay.
And where's the
So
next
surface mesh, the minimum size will be 0.002, max size will be 1.
one? 0.00. There you go. And then what's max size?
1 meter.
Okay. Growth rate?
You can leave that default.
Cool.
And then
Capture proximity is
yeah, capture and proximity, and then 12 degrees for the curvature angle.
And let's see, cells per gap,
So
1,
The,
edges, I think those are all
the
default.
two things we did before, the local sizing and then the create local refinement regions, at least the refinement region, is that for the volume mesh that we're going to?
Yeah, that would be for the volume. Both of them will affect the volume. So you generate the surface mesh first to kind of give you an understanding of what it looks like and what you're doing, and then you can make changes if you like see problems, because the volume mesh takes a lot longer than, because if you just generate a surface, a volume will be like 100 times however wide it is.
So the two operations we did before weren't necessarily for generating the surface mesh.
Yeah, I mean they did affect it. They affect both. So they affect the surface mesh in where the surface intersects with that. Because you can see, you can see the refinement regions on the surface mesh, because you can see how it gets smaller. If we didn't do that, it would all be the same size around the whole aircraft. And then you can see, you can't really tell too much on the trailing edge, but you can see the trailing edge is slightly different than the, but that,
That was the local size.
yeah, the logo sizing. So there's face sizing, which is where you select the face, and then you define the cells on that face. So that would actually be just for the surface mesh.
Okay.
It will affect the volume mesh, but it's defining the mesh on the surface. And then there's refinement regions, which is a volume around the body, which then you define the cells in that volume. And there's a lot more. There's like you can do it for edges. You can do it for a lot of other stuff.
The types of mesh controlling you can do is a deep rabbit hole of just whatever is applicable to your situation. The most common types for like aircraft stuff are like the region and the face sizing, and it will sometimes inflation layers.
All right. So now, does everyone have the mesh generated? Great. Yeah. Okay. So now we're gonna go to describe the geometry right below. And so first we got to define our geometry type. So it consists of only solid regions. No, because we have fluid. Consists of only fluid regions with no voids. Yes. So yeah, that's what we have no solid regions. So it's just gonna be a fluid region with no voids. Voids isn't like, because the aircraft is a hollow region with inside, but a void would be like gaps in the fluid, which I know it's kind of confusing, but that's just the way Fluent says it is. You would think that'd be called a void. Change all, yeah. So and then everything else you can leave default, and then click describe geometry. So now our geometry has been described. So now you get to update boundaries. And so since we named these beforehand, it's already defined for you. So you can see far field is pressure far field. And the far field is the spherical dome. And so that's where the air will be coming in. And we'll define that. So that's basically the inlet. The fuselage is a wall.
It is 4:05. Do we want to stop here? Save.
I say we can finish the mesh. It's only like a couple more steps. We're almost already done.
Are you guys good with?
Yeah, unless if you guys need to go, obviously you can. We'll have the mesh file to give to you guys, so you guys don't need it yourselves. We'll send it out. Yeah. So if you guys all are good to stay, I'll keep going. It's only going to be like a couple more minutes. So we have wall, and then symmetry is the symmetry condition. So then it knows that to double the values. And then the bodies on your aircraft are defined as walls. So that's how it interacts with the fluid. It's just defined as a wall, so it interacts the same as if you were to just do a straight.
So this is where the naming comes in. Earlier when we named different parts of the geometry, it's reading those names, and then we're defining what type of like boundary they are.
So now click update boundaries. So that should be quick. And then you have region. So this is defined as a fluid region, and we'll leave it as that because that's what it is. And then now we get to the boundary layer or the inflation layer. Do that real quick. So So add boundary is yes. And we're going to do this as last ratio. The offset method type. Number of layers, do 10. And then your first height is going to be.
Typically, you would calculate their first cell height. You're on yourself. How to do that is a little bit out of the scope right now of the class. We might go over that in the later class. But for now, we've pre-calculated it.
So your height's going to be this number. This 0.00016147. And so that's defined. There's calculators online you can use.
Here, zoom in so they can see that better.
What should the transition ratio be?
You can leave that as default.
Does everybody see this number? Everybody got this number?
Yeah, has everyone typed this in?
Cool.
Okay. Gonna move forward. So first height we have defined as this. And so we have it add in fluid regions and it grows off of the wall. So it's going to grow off of the aircraft and be added into the fluid region. So we can leave that and click add boundary layer. Boom. Now we get to generating the volume mesh. This is our last step. So solver will be Fluent. And then fill with, this is the shape of the cells. So polyhedra, kind of like octagons, we're going to use that. Growth rate, leave that. And then max cell height, I believe will be 1. Yeah. So define this. Actually, leave that as default. I just put 1.2 if you already changed it.
Yeah. If you already changed it, it's fine.
It doesn't matter.
If you the automatically calculated one might mesh a little bit better, but you could also.
Yeah, I think they put that there for a reason to give it a proper growth rate. So now we're gonna click generate volume mesh. This is the last step. It probably takes a couple minutes. So.
And hopefully it won't crash or have an error.
It's going pretty fast. So yeah, 20%.
It's a pretty simple mesh. So.
Yeah, it should be, I believe, 500,000. Well, I don't remember what I put for the max size, so it could be slightly, but it'll be around that. Because the max size really only matters for the cells out far, and they're not going to change the solution.
Like 500 pesos.
Yeah.
That should be about, yeah.
You already generated?
Yeah. Well, they all use 12 processors.
Yeah, no, yeah.
So.
And they probably have better CPUs on those. All right.
Almost.
You guys gotta wait for it. All right. Boom. I only have 400. Whatever.
You got 400,000?
409. Okay. So now we get the full mesh, and you can see, there's a section plane on here. So a section plane allows you to see throughout the mesh. So if you go up here to clipping planes, insert clipping planes, and it's like that, then you can see like at different points of the mesh. If you I have it as and need to see stuff, you can actually. So I'll show you guys the inflation layer real quick. So if you zoom into the aircraft body, you see there's now a small structured region growing from the aircraft, and that will capture the boundary layer.
This is the inflation layer right here.
Mm-hmm. All right. Well, and so you can see our mesh has a minimum quality of 0.12, which is above 0.08. So good job.
Yep.
Yeah.
Question?
Oh, it was the geometry consists of only fluid region with no voids, and then all the other ones you can leave default. All right. Any questions or anyone still having trouble? Because this is kind of the final step today. Tomorrow not tomorrow. Next Friday.
Yeah.
We're doing this every day, guys.
We're doing it so you can do it blindfolded.
You don't need to. I'll provide if you guys want to save it to use on file, you can. But I'll upload a file onto that shared.
So if you save it onto your OneDrive, so it's a little dangerous to save onto this computer that you're working on right now, because they like to delete stuff off of the computers. They really want you to only save stuff onto your OneDrive. The danger of that is Ansys really does not like to read things off of the cloud. So if you want to open it back up, you'll have to pull it off the OneDrive again if you want to use it again. Or if you don't want to bother with that, we have this mesh pre-generated already, and we'll give you guys that mesh next time so we can go ahead and get onto the actual solver. Either way, it's fine.
I think definitely, since we got meshing done today, we'll be able to do the solver in one day, and then we can do a new topic on the third day.
Or go into more detail or whatever you guys have.
You would go to File, Export, and then Mesh, and then just save it wherever you want to.
Yeah.
Is there any topics you guys would want to cover on the third day? Like, so one thing I think is internal flow. So like flows within an engine. We could do supersonic flows, so we could see like the shockwave formation. And we could do supersonic and transient, so then you can see the time dependent, and you can see like videos. Yeah, transient. Okay, there's a lot of interest in transient, and so transient we can also couple with something else, guys.
Mhm.
So, is there any other things someone would want to see?
We might like already have, if we, on the third day, if you want to do something like transient, we might just give you guys a meshed thing already. to
Yeah,
work
yeah.
with.
Since we already kind of now we know how to mesh. Now in the future one, we could just do the solver, and then
Mhm.
yeah. And also, if you guys want to like do this on your own time, like if you are really interested in this, there's a free student version you can download on your laptop. That's what I'm using here. It's just, if you just look up Ansys student download online, it will pop up and you can download it. Click the like link at the bottom so you get a scam. But
Yeah, and also if you just look up Ansys tutorials, if you want to practice on your own, Ansys has plenty of tutorials. There's also just tons of people who have uploaded YouTube videos as well.
yeah, if you go to the Ansys website and innovation space, they have like tons of free tutorials. This is kind of where I got the geometry from, but covering all topics, fluids, if you want to look into CFD, and the stuff covering transient, supersonic, internal, any type of flow you'd want to know about.
Yeah.
Oh wait, this is just like tech support. Actually, I clicked the wrong thing, but they are a tutorial somewhere. All right, well, that's everything, guys. If you guys need to head out.
If you want, look into AIAA, look into ARCT, rocketry. I know most of you are already in ARCT.
2.1 million. I was like,
Oh wait, no, the cells are determined by it. I thought you were asking how fast it
Wait, did
generates.
you said
He's saying he got more cells because of the cores.
you had 2.1 million cells?
That means you put a setting in wrong somewhere. But
Yeah, you
it's
put
okay.
something in that's way smaller than normal.
that's not so